Hello everyone. A few words about me. I've been working with Erlang for nearly 5 years and in recent years with Elixir too, and have been involved in developing continuous load testing tools recently, and that's how I got into chaos engineering. And today I would like to tell you a little bit about orchestrating mayhem. And before I start, I would like to ask a question. If there's anyone who have heard of chaos engineering, please raise your hand. Okay, quite a few people. How many of you have applied it? Okay, not that many. I can see 2, maybe 3 hands. Alright, so I'm hoping it's gonna be interesting to you. I would like to start off with some what, why and how in terms of what the chaos engineering actually is, why bother, and some basic techniques of how to apply it. And actually from this talk my goal is to simply introduce the idea and encourage you to go and try some basic principles and to see whether it's something that's worth investing in when you develop your systems. If you look at today's systems, you may think that they are quite complex, especially when it comes to microservice architecture, when to serve a single request, multiple services are contacted. And what's more, it happens that different services are being developed simultaneously and they are being deployed at the same time, let's say within a day. And that's why we can say that chaos, as it is inherent in large distributed systems. And even if the individual services function properly, they are tested by the teams that ship them, then they are integrated at some integration software, and then they are deployed. The interactions between them may lead to some unpredictable outcomes when they are in production, and especially when compounded with some real-world events like server crashes, net splits, disk failures, and such. And to give you an example, let's consider the graph above, where we have a client that hits microservice A, which in turn contacts microservice B, C, D, E, and at some point C fails and we have a fallback in place, which is F. But it turns out that for some reason F is not able to handle the load that C was. It builds up a queue and eventually fails. And chaos engineering is about experimenting on a system to provoke scenarios like this one, so that you can learn the system behavior in turbulent conditions, ideally in production. And this is the formal definition of what chaos engineering is. So it says that it's a discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. So it's empirical because it's about experimenting, it's about learning system behavior because it says about building confidence, and finally it's about experimenting at scale because we are running experiments in production. And this example could be a valid chaos engineering scenario in which we deliberately disrupt C to learn the weakness of the fallback F. And now, why bother at all? What's the rationale for chaos engineering? First of all, it's to build trust. As I said, today we have great development velocity, piece of innovation, and it may happen that one person is no longer able to capture the whole system, and that's why there may be no trust in what we ship into the production, and by experimenting you want to build that trust over time. Then it comes proactivity. And it means that we want to be proactive and discover weaknesses before they manifest system-wide. We would like to capture them in some sort of controlled environment. And finally, it's cheaper because we may prefer to put some fraction of users at risk than to experience the entire business taken down that would hit all our customers. And before I get to some principles of how to apply it, just a note about a steady state. Steady state refers to some property of a system that it tends to maintain over time within a certain range of values or according to some pattern. For example, we can say that a human body has a property that it keeps the body temperature at some level, and we say that our body is in a steady state where our body temperature is at that level. It functions normally. And the graph above represents steady state of some system where we have request response time around 40 milliseconds. And that's something we have learned over time by observing our system, and we know that when this property holds, our system functions normally. And then we have another graph of the same system representing the same metric, but this time we have some spikes. And because in the first place we have learned what the steady state is, now we can say that our system is no longer functioning normally. Something wrong is going on. And having that said, chaosprinciples.org, the same site that where you can find the definition of what chaos engineering is, defines some 4 basic steps of how to practice the discipline. And the first step is you need to learn the steady state of your system. So you need to observe it over time, pick some key business metric that is, let's say, related to the money the business is making, something that is very important, and get to know what the normal state means for your system or the business. Once you have it, you set hypothesis. You hypothesize that the steady state will continue when you break something in the system. And here's where we have the third step, which is about introducing some variables like real world events like server crashes, disk failures, and so on. And once we introduce them, we can learn something about the system. Either we can learn that it's not able to cope with the failure that we are introducing, or it did it well. And the last step is to try to disprove the hypothesis by comparing the steady state with the learned behavior. So we are comparing the same metric, but one was that we learned by observing its normal state, and the other one is refers to the situation when we introduce some fault. And we also have something that we call control group. So this is the set of users that hit our system when it's in normal state, or this part of the system that is not affected by any fault. And then we have experimental group, which represents the set of the users that are affected by the failure that we are introducing. And now I would like to tell you how Netflix does it, who practice the discipline. And let's assume that they would like to answer a question how their API handles failure of rating service. And the normal path of such a request would be that the client hits the gateway, then the gateway calls API, and finally API calls the rating service. Rating service is some service responsible for assigning scores to movies, something like that. And because they observe their system, they know what is their key business metric, they know the steady state. And then what they would do, using Chaos Automation Platform, that this is the tool that they use to run chaos experiments, they would spawn 2 additional API clusters, one for the experimental group and the other one for the control group. And then, using the same component, they would instrument the gateway to direct fraction of the request the normal path, the blue ones, and some fraction to then they would decorate some fraction of the requests to go through the control cluster, and finally some fraction of the requests to go through the experimental clusters. Then would scale these decorations appropriately, and finally they would enable some fault at the experimental cluster, which would be simply drop all the codes from the experimental cluster to the rating service, so that all the customers that go through the experimental cluster are affected by this injected failure. And that was the first part, which discussed some basic and high-level concepts. And now I would like to tell you how we at Erlang Solutions apply these principles to one of our systems that we develop, and share with you some learnings that we have gained from the experiments that we run. First of all, what we do, we have a Manguzayan server, which is a messaging service that allows clients exchange messages, which is used, for example, to build internet communicators, and it can run in a distributed mode, and then we have a cluster of nodes, and this is first possible place where something can go wrong. I mean, there's an interest. This is interesting for us because we may have a net split, and let's say the node are no longer able to synchronize. We also can talk to external authentication service, and this is another this is another potential place to experience some failure. We also have a database which is used to archive messages, and again, for some reason we may not be able to write to this database. And finally, some installations would stream records of users' activities to some streaming service like Kafka, and again, this is another potential place where we expect some fault to happen. And this is a set of injection points, so places in our system that potentially can introduce some problems if something bad happens. And this is the base for us to set some hypotheses, like if something bad happens on, let's say, the connection between the nodes in the cluster, we assume that something, and we would like to try this hypothesis. And we simulate failures by injecting some code into the running Erlang VM, or by directly tampering with the servers that run the services. And to carry out these experiments, we use our load testing infrastructure. What we have is a load testing scenario that we fed our load generator with, which in turn puts some load on the server, and we learn the steady state. And this is our control group. Then we use the same load testing scenario to run another load test, which is the experimental one, but this time we inject some faults into the running system. So our approach is a little bit different than the one from Netflix, because we are spawning two separate load tests that I configured the same way, and we compare the steady state from the control load test with the metric that we have gathered from the experimental load test. And now I want to share with you 3 hypotheses we have tested. First one was related to a database failure, and we said that failure to write to the database won't disrupt the service, the basic functionality, which is that the users can exchange messages using the server. And as I said, the database is used to archive messages, and in the system we have worker processes that keep connection to the database and a supervisor process on top of them. And to simulate that failure, what we would do, we would kill the entire pool of these processes at interval and see what happens. And this is an example code that we used to do that. So what we did, we define fault fun, anonymous function that represents this fault, and what it does, it grabs all the worker processes from the supervisor, then steps over them and kills them y1 at the interval, and then calls itself recursively. And to enable this fault, we get this fault fun, spawn it on a node that you would like to affect, and when it's done, we simply kill the process that was simulating the failure. And what we learned from this experiment, this is the request response time of our service, and this is where the chaos started. This is where it stopped, and the service was not disrupted. So we proved the hypothesis. So we learned that even if the database is not available, we are still able to serve users. But what we have learned was that the performance turned out to be better. I mean the key metric that we are looking at. And it turned out that when the pool of workers connecting to the database was not available, the reads and writes to the database were simply dropped, and that's why we saw lower load on the server. That was the first experiment. The other one was the hypothesis that we said was delay on the connection to the authentication service won't prevent the users from logging in. So we said the hypothesis that if for some reason we have a delay on the network to the authentication service, the users eventually will log in. And similarly, as with the case with the database, we have internally we have a supervisor and a pool of workers that call the authentication service, and to simulate this delay, we added it at the workers level. And to achieve it, again, we defined a function. Basically, we used the mocking technique. So what we did, we put a mock instead of the original module that was calling the authentication service, and added artificial delay. So what we did, we defined a delay auth function that take user and a password, and added some sleep so that we have this delay in place, and then we would call original function that eventually calls the authentication service. And then through mocking, we would replace the original authenticate function with the one that we made up that had the delay in it, and set an expectation on a mock so that our function is called every time a user tries to log in, and finally when we are done with the experiment, we would unload the mock. And here the steady state was that eventually during our load test all the users log in, but this hypothesis was disrupted because, as you can see, these two lines, these are the not affected nodes. We have 3 nodes in total in this experiment. The not affected nodes had users, but the one we ran the default on had no users. It turned out that that small delay caused that the users were not able to log in, and what we learned from it was that there was no proper retry mechanism at the load generator level, because we would expect that eventually, because there was load balancing in place, all the users get into the system, but it didn't happen. And the last hypothesis we test. We said that if there is a network glitch on the connection to Kafka, which is the one of the streaming services we use, so that all the records of users' activity are logged. If there is a glitch on this connection, eventually all the messages will be delivered. So our server connects directly to the Kafka server, and to simulate this failure, we used IP tables. We simply installed the rule that would drop the packets, the incoming packets from our server. And we wrapped that rule into our Elixir code that we use to represent defaults. So we would literally add a rule to an input chain of an IP tables, and that run that command on the server that was running the Kafka service. When we were done, we would simply remove that chain remove that rule from the IP tables chain. And our steady state here was that the number of messages produced by our server equals the number of messages consumed from the Kafka server. And what happened was that we produced one message, and then because we didn't get acknowledgement, our application retried to send that message 3 times, and then the network recovered, and on the side of the Kafka consumer we've got 4 messages, and this time our hypothesis was disrupted again, because we produced one message, retried 3 times the same message, and we've got 4 messages. And we learned that it was the Kafka driver which had its internal retry mechanism, and we were like doubling the retry. So first we produced a message, there was the connection was broken, it was stored in the Kafka queue, and then every retry from the application layer was treated as a new message, and that's how eventually we've got 4 messages. And these were the basic techniques, and now how to actually get them executed. If we have coded them, like here with Elixir, we have a few options. So one is you can get into your shell and simply type it in, but it's not handy if you would like to automate the process. That's why we can make use of RPC, which comes with the Erlang VM, and we can instrument our faults by calling the node you would like to affect. And we could also wrap our faults into an anonymous function that you would then spawn in a process on the affected node. These faults could also be weaved into the code and triggered by some metadata carried along the messages that are exchanged by the users. But that is not the approach that was solution to our problem. And this brings us to the last part of this presentation, which discusses how we attempt to automate this whole process. Because in the first place, we were applying these faults manually by logging into the shell and typing in these faults, or let's say in a semi-automated way. And we took an attempt to automate the process. And just to recap, we carry out these experiments by running 2 separate load tests, and then we compare our key metric and judge whether we have some problem when there is a fault in the system or not. And this is what we treat as a chaos experiment. And then we develop a tool that would automate our chaos. We call it Typhoon. And this is an Elixir application that comes with a front end, and which is Typhoon Web, and the backend Typhoon, that consists of 3 components. The first one is chaos manager, that is like orchestrates everything, and then we have fault injection, which is responsible for managing the faults, and finally we have infrastructure, which orchestrates the load tests. And the infrastructure component comes with 2 models: the test setup, which defines how the load test should look like config files, what Docker images to use, how to scale it. And the infrastructure component would talk to our load test automation tool to spawn a test, to get notifications on its status, and to get notification whether it's whether it failed, whether it's done. And it also has test topology that defines some metadata of a test itself, like what are the IP addresses and ports, what are the services name when the test runs. Then we have default injection that comes with a fault protocol. Technically, it's an Elixir protocol, and that's our main extension point, meaning that we put an effort to make it easy to add new faults to the system, so that if we discover any other injection point that would be useful to test, we can easily add it. And the fault injection also talks to the load testing infrastructure to basically inject these faults, either by running some code at the node to be affected, or by tampering with the system that runs some service you would like to disrupt. And finally is the chaos manager that defines the experiment model, that has a reference to the control load test, to the experimental load test, to the setup, to the faults, and faults offsets, which define when in time the faults are to be injected when a particular load test run. And we would start an experiment by providing some configuration through a web form, and then we would build an experiment and run, and based on that build the setup, run the control load test, and that's how we learn the steady state. And then we would run another load test, which is the experimental one, inject faults as it is running, and finally learn behavior and compare the two. And now some Elixir bit. And as I said, we have a fault protocol which provides a single API for all the faults, and for now it just has one function, which is apply, which takes the fault struct, so a data type representing particular fault, and a reference on a test, so that we know at which test to apply the fault to. And if we implement the fault, we need to implement that interface basically. And this is an example fault, and here we also use embedded schema and change set to make it easy to validate parameters that come from the UI, so that it helps us to build default struct. And as I said, each fault needs to implement default protocol. And this is basically all I have for you. We talked about chaos engineering as a concept, and then I showed you some basic techniques how to apply it, and finally our journey to automation. And I encourage you to go try to explore it and see how it works. Try to apply some basic techniques to your system, and if it works for you, try to put it into your continuous integration pipeline and benefit from it. And that's all I have for you. Thank you.
I must admit something. When you asked at the beginning, has anybody ever done chaos engineering, I didn't raise my hand, which was a mistake actually, because it turns out that I actually did it, I just didn't know the right name for it. My question is about Typhoon. Is it something you did for yourself, or is it available somewhere? Or is it your internal tool?
No, it's the internal tool we are working on.
Okay. And another question about Netflix. Am I right that they experiment on the live system, on the real users?
Yes, they do.
So the test fails when users start to complain or something? How do they measure it?
So as I said, so at least that my knowledge is based on some blog posts from the previous year. So what they would do, let's say they want to test some component, they would spawn additional 2 clusters of this component, one for the experimental group, one for the control group, and then they would just put a fraction of users to both of them, so that to minimize the blast radius. And then these two new clusters report the some key metric that they measure, and then when the experiment is done, they compare the two and they know whether something went wrong or not. That's how they do it.
Hi, here. How much time do you need to spend on the design of the actual production system to make all this possible? Because we saw that you are injecting some like specific logic to create faults or to add new behaviors. Mm-hmm. At what moment do you decide when to actually change the production system to do so?
Mm-hmm. So the question is, if I understood correctly, how long I spend on designing these faults and how much effort put into it. So
not so much the faults themselves, but for the production system to allow injecting the faults. Mm-hmm. So in Erlang, like it might be easier, but maybe in other technologies, it's not that easy to change dynamically the behavior of the system. You know, in production, you'll have to make a new release or stuff like this. But
okay, so the question is how long it takes to adjust some system so that it's able to run some faults in it.
Yeah.
So in our case, what I was presenting, there was no change required at all, because we were injecting anonymous functions in the running system. So no change, no recompilation, nothing. That was our approach. Mm-hmm. But another way to do it is to weave some triggers into your system, and that would require a recompilation, rebuilding, and another release with some code added that would react on some metadata carried on with the request. So in our case, we were running the same system, the same code when experimenting and not experimenting. We were using anonymous functions.
Okay, thank you.
Injected into the system.
Simon, I wonder if you can share a little bit about how you stress test specifically the message broker and the container scheduler.
We are not specifically stressing. You mean the container scheduler in context of Docker?
Yes, you mentioned Docker.
Yes.
And Kafka as the message broker. So my question is, how do you apply these chaos engineering strategies in the context to stress test those parts of your architecture, the Docker container scheduler and the Kafka message broker?
Okay, so our aim is not to particularly see how it to stress the Docker scheduler. We try to customize everything so that, I mean, on the Docker level, so that we are able to put the load we want on the system, and once it works, we have it's like a part of our scenario. That's the part of the configuration, how to customize the Docker containers. And what we actually do, if there's something special we do, is we are pinning a CPU cores to some containers to improve performance. And then once we have a stable load tests that yield repeatable results, then we apply chaos engineering principles to these load tests. So this is first we stabilize the load test as a whole.
Okay, if I am getting you correctly, you are saying that in the Docker case, you are running one container per CPU, so you are bound to the CPU that you have on that particular machine, or I guess the amounts of containers that you run on the scheduler in your cluster is bound to the amount of cores that you have on that particular cluster. I'm getting that right, or I'm completely wrong? What I'm trying to get here is trying to learn about your experience with multiple Docker containers, like with multiple Yeah, Docker container, basically, that's it.
Okay.
And it's not in the context of Docker by itself, but in the container technology as a tool, basically.
Okay, so it's not like that we are pinning one core to container. What we do, we know how many cores we have on our machine, and then what we do now, we simply assign the number of cores evenly to the containers we have on the machine, so that they are not overlapping. Because when we allowed all the containers take all the cores, we were seeing some performance degradation, and then we customized it so that every container has a range of cores to use, and it helped a lot.
As I understood, the failure that you prepared and that are controlled by the Typhoon, right? It's a failure of the particular element of the system, like the internet connection to server one or another.
Yes.
Did you check the interactions between the failures? I mean that something is broken and then something else is failing, or is it just a one by one test?
For now, it's one by one, but the intention is to compose these failures so that we can test what happens if two of them happen simultaneously.
Yes, you know, the planes goes down when two things fails. The planes are designed to, I mean, when you have a plane, it usually handles well one failure, right? The problems becomes when there is another one. So your system could be also expose some problems when you have two failures in the same time.
Yeah, that's perfect. That's perfectly correct. That's what we are aiming at, to be able to run multiple failures at the same time, not one by one. That's just the first step to discover some weaknesses. Once we have them, once everything seems to be working fine when we apply the failures one by one, then we start experimenting, applying these failures, like mixing them together and things like that. That's nice remark. Thanks.
Hi, so are you aware of any technologies on the infrastructure level that would support fault injection? I was like thinking some service mesh or like anything similar. Because your approach depends on the Erlang platform to inject faults, and I thought it would be nice to have it on the infrastructure level.
So I presented one thing that we utilize IP tables to block some traffic. I also know that there is don't remember the tool name exactly. Maybe something like Netem. I may be wrong here. That allows you to put some delay on the network interfaces. And I also know that in case of Docker, there is a tool called Blockade, I think, that also allows you to tamper with the network level. And Netflix also has some open source tools on their GitHub that you can check and see if they apply to your use case. But there are some tools definitely that allow to do things like that.
We have time for one more question. Okay, so unless I'm missing someone, I think we'll end here. Thank you, Szymon.
Thank you.